Welcome, ladies and gentlemen, to the public forum of the group exhibit Hydrogen Fuel Cells and Batteries. You're well welcome to take a seat, have a drink on the house, and participate in the next discussion about the world's first light-activated fuel cell. What that exactly is will explain to us the chairman of Enocell Limited, John Lidderdale. Here he is. Give him a big hand.
Thank you.
John, good to have you here.
Thank you. Good afternoon.
Good afternoon to you. We would like to know a little bit more about Enocell. It was founded at the University of Aberdeen in Scotland in 2011 to commercialize the photocatalysis research of Professor Donald McPhee, who is around. I can't see him at the moment, but he is around somewhere. So first tell me, what is photocatalysis and what did he find out?
Well, photocatalysis is the effect of light on various materials in different circumstances. Here he is, he's arrived.
He is very good.
what Donald discovered that triggered this whole process was that tungsten trioxide in a water environment, an aqueous environment, if you point the right light at it, will oxidize itself from the water effectively, and that was a benefit. He was not working on fuel cell research at the time, but he realized that it has application because he's a smart guy, and so that's how it's ended up affecting fuel cells.
So what I've heard in science, photocatalysis is at the moment a hype theme, a hype topic in the science community. So is it to put photocatalysis also into fuel cells, or was it a real discovery?
No, it didn't start with the photocatalysis. The photocatalysis was discovered in relation to water treatment process. What the thing that was clever that Donald did was realize that it had applications in a different technology completely. So it wasn't, let's look for something glamorous to do with photocatalysis.
Okay, so explain that to me. So in a fuel cell we have, well, we also have water, of course.
Yeah.
And we have a catalyst in there. And there's a problem with the catalyst.
Yes. The essential issue is that carbon monoxide acts as a poison to platinum, and that's very well understood. And one of the solutions to that, one of the things that's been understood for a very long time, is that certain other co-catalysts can be used to oxidize carbon monoxide and turn it into carbon dioxide, which then it disappears down the gas stream. And so one of those is tungsten trioxide, which several people have used a number of times. What Donald discovered is that tungsten trioxide in a water environment, which is the middle of a fuel cell, you're making water, with the light attached to it, would reoxidize the tungsten trioxide. So you end up with a virtuous circle. So the tungsten trioxide oxidizes the carbon monoxide and turns it into carbon dioxide, but then re-equips itself with more oxygen out of the water.
So you have the same amount of carbon monoxide and carbon trioxide in the water of a fuel cell, so that fits together? The two elements?
Yeah, well, without turning it into a technical discussion, the simple thing that happens is carbon monoxide gets turned into carbon dioxide by the trioxide in the tungsten. That depletes.
With the help of light.
No, the tungsten trioxide will oxidize carbon monoxide while it can. It then becomes depleted and can't do it anymore. So what the light does, because the water's there, is to put oxygen back into the tungsten trioxide. So it's able to start again. So you go round in a loop.
Okay, but you need the light for that?
You need the light.
How do you get the light into a fuel cell?
It depends on the fuel cell technology. First of all, this only is relevant in low temperature fuel cells. At the moment, we are focused on methanol fuel cells and PEM fuel cells. There are other low temperatures. That's where we're focused. And we use slightly different technologies because a methanol fuel cell, the membrane in the middle is much thicker. So in essence, it makes it easier because it's easier to get thicker things than thinner things, if you follow me. So we use a glass fiber technology in the methanol membrane. We use a polymer membrane or polymer fiber in the PEM fuel cells because they're much
fiber is
thinner.
directly in the membrane. Yes, it's not outside.
No, it's inside the membrane. In the Nafion layer in the center, we lay onto the Nafion layer the light dispersion devices that we're using, and then the light comes in from outside the cell and is dispersed in the so at the point of chemical reaction is where we have the light.
But you need to have this light in any layer. So,
yes,
so
each
only every two or so, but any layer.
No, every single cell has light in it.
So as I've heard, in a normal stack for a fuel cell cars, there are 500 layers in it. So you need to do that 500 times.
Yes, but it's not 500 individual lights. You have 500 individual dispersion devices, but they might be powered by 1 or 2 lights.
Okay, the dispersion devices are just the fiber, which are part of the membrane.
That's correct. Yes, so, effectively.
So it's like the glass fiber, which can transport light easily from the outside inside. So just at the outside of the fuel cell, you need some light source.
We need a light. The thing that is slightly tricky and has taken some time is that fibers are designed. Optical fibers are mostly designed to transport light down their length. We don't want that to happen. We want it to come out.
Spread out.
Yes. So manufacturers of light go to an immense amount of trouble to try and stop it leaking, and we want it leaking.
Right. Yeah. Very good. But you managed to do that.
We got that. Yes.
So there's light. In direct methanol fuel cells and PEM fuel cells, but you told me there's a slight difference between the two for the light transportation.
Well, yes, essentially we could use. It's slightly cheaper to use glass fiber where it's possible to use it, but glass fiber it's really hard to get down to tiny sizes. It works well with methanol because the membrane is a very large amount bigger, so that works fine. But at the moment, although we are working with people like Corning, for instance, we're working with the manufacturers of the fiber to see if it's possible or to what extent you can get fiber thinner, glass fiber thinner. But you can get polymer fibers quite a lot thinner, 9 microns, numbers like that. So that's more appropriate as we speak, and they both work well. And it might, we are actively using fibers at the moment. We're also investigating more solid structures which we then cut with lasers or something like that. But the production direction is fibers.
But isn't that very costly to get these fibers into a fuel cell? So the cost of the fuel cell will in the end be much higher than a normal fuel cell without this fiber?
The truthful answer to that is we don't know the truthful answer to that. But what we do know is, what we believe the end answer will be is because you will end up needing a lot less platinum or platinum group metals, and what we substitute is less. So we take out a lot of expense, but we add some complexity. And we believe that probably in terms of the cost of a stack, there'll be a zero net benefit in cost. But you can now use a fuel that's about 20% of the cost of the ones you presently use. The stack life will increase an absolute minimum of 30%. And so that's an empirically arrived at figure, but we believe the number is probably it will extend the life 3 times, numbers like that. So the benefits are elsewhere.
So 2 big advantages, if I got that wrong. You don't get this poisonous of the catalyst by carbon monoxide. So you need less platinum for the catalyst. And the other advantage is you can use different kind of hydrogen, not so purified hydrogen. You can use chemical hydrogen then from chemical processes.
That's correct. Yes. The biggest single advantage is you can use what is in fuel cell terms really dirty hydrogen. So you can, I mean, hydrogen used for welding purposes, for instance, works fine. And it is literally about 15 to 18% of the cost of the ISO standard hydrogen that's specified for most fuel cells, and that's over a life of a system. It's huge, and the other huge advantage over time is you replace the stack probably a third as often as you presently have to, and that's an immense advantage. So if the capex works out the same, we had a consulting group do what the Americans call a bumper-to-bumper exercise for us, so cradle to the grave, if you like, and their calculation, a company called Element Energy, some of you may know, but their calculation was that the overall saving could not be less than 33% on the life cycle cost. So that was encouraging.
So how long could you test your fuel cells already?
Well, at the moment, most of our testing's been done to 1,000 hours. We have testing going on at the moment that's gone, but 3,000 hours is the longest test we're planning right now.
There was no degradation then?
So far, no degradation.
Perfect.
Yeah. There's always the difference between empirical and calculation. The calculation is we should get no degradation for a lot longer than that, but we can only prove that when we've been around long enough to prove it. Yeah. So yeah.
Are there any questions from your side? And just raise your hand. I'll be happy to come with a microphone right to you. That's not the case. Most people are fascinated by that idea, of course.
Okay.
So how far are you, John? You completed research, obviously. You're starting developing now products.
Yes, we'll have our first product will be a DMFC product, and the DMFC product is due to be the first one's due to be in the customer's hands in the last quarter of this year, 2017. And the first production unit of a PEM unit is due to be in the customer's hand exactly 12 months after that. So that's where we stand. We have 4 prototypes where we have we have customers for them at the moment, and they are, I have to say, they're friendly customers in the sense that they know they're getting prototypes. And
what I've learned is you also have a development agreement with Hydrogen.
That's correct. Yes, we have an agreement with Hydrogenics, and who are here as you mostly know, and so our initial agreement with Hydrogenics is they effectively get first mover advantage with our equipment. But they're helping us immensely so we're not designing a stack, we're putting our equipment into a Hydrogenics stack. So the only production design changes that have to be made are just to accommodate what we're doing.
So John, you don't have a product so far, but you're developing. So you're still looking for partners for developing.
Yeah, we're looking for production partners for further down the road, and we're really interested in talking to people who have technologies either that they've proved or are confident in that would complement, or what we do complements them, if you see what I mean. We were having a conversation on our stand not very long ago and we were saying, if you go around all of the new emerging elements you could build a brand new fuel cell just by putting them all together, if you understand me. And some of those we're obviously talking to, but some of those are extremely relevant. But one of the things that happens, I mean, I've been doing this a very long time, so forgive me if I sound a bit like Grandpa, but one of the things that happens is that too many things happen in isolation. People have a really good idea, and they develop it in isolation, and they don't go and talk to people where it has a direct, or might have a direct impact, a benefit to them. And very often that can take, I mean, that's why we're talking to hydrogenics, because otherwise we spend 6 or 8 years developing something hydrogenics has spent 30 years developing. You know what I mean? And I would urge people here to look around for people they can partner with, and we would love to partner with people where they have a thing where we would help them.
Also for me, I'm not a scientist at all, not a technician, but I'm here on this group exhibit since 23 years already, so I also sound like a grandpa maybe, never mind. I've never heard about this photocatalysis for the first time, so it's very important that you spread the news here on the group exhibit and let everybody know, okay, we have a solution for these poisons on the catalyst.
In fuel cell terms, it has the potential to be a complete game changer. At the moment, everybody in this room, everybody in this audience knows a fuel cell is the most efficient way of converting a fuel into energy. So why isn't the room full of fuel cell billionaires? And the answer is, I mean, I hope to be the first, but the answer is because they cost too much to buy, to acquire. The fuel for them costs way too much, and the stack, the engine, if you like, doesn't last long enough.
All three problems you have solved, you can really say. Yeah.
That's yes. I mean, there are. All of us are aware of any number of companies who've been trying to solve those problems within the supply chain, but we're trying to solve them in the fuel cell, if you follow me. So don't. At the moment with hydrogen, for instance, people spend an immense amount of money making the hydrogen purer. I'd rather spend a lot less money making the fuel cell able to take the hydrogen without all that expense.
Right. And there's a lot of this kind of hydrogen, like byproduct hydrogen from chemical industry, which is not used now. It's just burned into the air.
We have a supplier we're talking to. It's part of the Exxon group, and they have a gas fractionation plant in Scotland, and it is presently venting to atmosphere, or flaring actually, about 4,200 tons of hydrogen per year, and it's working half shift, by the way, so it's working 12 hours in the day, and their hydrogen is at less than 1,000 parts per million CO, just under 1,000 parts per million, and we can use that. So you know, it's an order of magnitude cheaper than the stuff you can buy from Linde or Air Products or one of those people.
Thank you very much, John, for talking to me. It was a pleasure to have you here on stage. And who else wants more information, just visit John at his booth of Enocell at C52, which is just down the aisle. I would like to thank you very much for being here and you for your attention. Thank you very much.
Thank you.
And there's another interview coming up right now here at 12:40 on our main stage with Marieke Rejald. She is the Executive Director of the European Hydrogen Association. They will talk about clean hydrogen for all Europeans. Please stay tuned, have a coffee or tea on the house, and listen to our next talk. Thank you very much.